Welcome to another unit in this workbook, Statistics. This time focusing on the multiple linear regression approach and how we can calculate the coefficients in the case that we have more than one independent variable. In this case, the regression line will look as follows, with b0 being the intercept. Then we have the different independent variables with their coefficients b1 till bk, under the assumption that we have exactly k independent variables. Well, how can we determine these parameters b0 till bk? Well, in the first step, it makes sense to write this in a more compact way, in a compact matrix vector notation way. So it looks like this. Like this, where y is the vector of all the y values we have, and x being the matrix containing all the values for our independent variables, and one column with only ones, which represents the constant, which represents the intersect. Finally, b in this case then is the vector of coefficients, the one we want to actually determine here. So in other words, we simply have to take this system of equations and find the solution which leads to the best fit. So to first illustrate this with a little bit of data, it could be something like this for a situation where we have five observations, and k being 2, so we have two different independent variables. Then this is the column representing the intercept, it's only once. This is the column representing the values for the first variable, so those are the x1 values. That's the column for the second independent variable, so that would be the column for x2. Here we have 1, 2, 3 different parts in our regression line, so we have 3 parameters we want to calculate. b0 for the intercept, b1 for x1, b2 for x2. Okay, so much for the general notation way. How do we go about calculating the best fit, the coefficients which describe the best fit? Well, we first off consider the difference between the inputs, that's the right side, and the outputs, which are the dependent variable. So we simply calculate this part, and then we're going to, well, not really square it, but use the matrix vector equivalent to a square, which is multiplying the transposed with the expression itself. This acts like the square of the difference. Well, that's similar to what we did in a normal simple linear regression way. We take the difference between y and the estimated values, so the regression line. We squared the result. That's more or less then here the matrix vector equivalent. This case we factor out. Factoring out again with matrices and vectors looks slightly different. And we solve this. We first derive for the parameter b. Here, parameter b is more or less the whole vector of our solutions. And then we solve for b. So that's the derivative for the vector b. And then we can solve this system, this equality for this parameter b, this vector b. This case, well, we see we can simplify this by first dividing by 2 and bringing this part on the right side. Then looks like this. Now the problem is we would simply divide by this part, but we're not allowed to, because you cannot simply divide by matrices. So we're going to multiply this with the inverse of this expression. And it looks like this. So here, that's actually the solution for our vector b. Vector b in a way that those coefficients minimize the squared difference between actual values for y and estimated values for y. Well, that's everything there is to the classical multiple linear regression approach. The only difference, you have to replace the classical I take this coefficient that and derive for this, solve for this with the respective vector or matrix operations. And the same goes for the squaring here as well. But the general idea is following exactly the same lines as we had when we talked about how to find the solution parameters for a simple linear regression. You also see the main problem here in determining this solution, especially if you work with a computer, because calculating the inverse usually is not the most efficient way to find a solution, and it's also a relatively unrobust way. So small changes in the calculations might give you a totally different result. So that's actually not the best way in doing this as it's written down here, but it shows that a solution can analytically be determined in this case still. Well, as I said, that's about it on multiple linear regression. I hope you enjoyed this short session. I say goodbye and see you next time.